Okay, let's dive in. Imagine building something incredible, layer by layer, like with 3D printing.
Right.
Now, picture trying to do that not with easy-to-melt plastic, but with materials that can survive scorching heat, materials tough enough for jet engines or even medical implants.
Yeah, we're talking ceramics.
Exactly. And printing with ceramics, that opens up a whole new world of challenge and, well, possibility.
It really does. Forget traditional ceramic manufacturing, the high heat, complex molds, pressing powders. It's pretty involved.
Yeah.
Additive manufacturing or 3D printing, it promises this ability to create shapes so intricate, so customized, you just couldn't make them any other way.
That sounds tricky.
Oh, it is. Applying that layer-by-layer idea to materials that are brittle, start as fine powders or maybe thick pastes, and need intense firing to become solid.
Yeah.
Yeah, that requires some serious ingenuity.
And that's our mission today on the deep dive. We've got a stack of fascinating source material focusing heavily on one specific approach, a technique called robocasting, drawing a lot from a really detailed PhD thesis on the topic.
Right.
Our goal isn't to get lost in every single technical detail, but, to pull out the essential knowledge, find those surprising aha moments, and figure out what's truly important for you to understand about this cutting-edge field.
It's about taking this complex piece of research and translating it,
Yeah.
making it a clear picture of the fundamental science, the engineering hurdles,
Yeah.
and the exciting potential applications.
Absolutely. So over this deep dive, we'll get a sense of the whole landscape of ceramic 3D printing first.
Good idea.
Then we'll zero in on robocasting, how it works, what makes its ink so special, and there are some truly weird properties we need to talk about.
Oh yeah, the rheology part is fascinating.
Well, why printing even simple solid parts is surprisingly tricky, and finally, how this technique is being used to create advanced ceramic composite materials, some even inspired by nature.
It's a great journey connecting basic material behavior all the way up to advanced structural design.
All right, let's get started. Stepping back a bit, the source material makes it really clear that ceramic 3D printing isn't just one single process.
No, not at all. It's more like a family of techniques. They all do that layer-by-layer build, sure, but in very different ways.
How do they group them?
Well, you can broadly group them. Some methods work with a bed of fine ceramic powder, right? Using a laser or maybe a binder to solidify layers within that powder.
Okay.
Others, like fused deposition for plastics FDM or the robocasting we're focusing on, they extrude material directly. No powder bed.
And I imagine the choice of technique really dictates what kind of shapes you can actually make.
Precisely. The source highlights how different techniques handle geometric features differently. Things like printing overhanging structures, creating internal cavities, or bridging gaps.
Makes sense.
If your method involves a powder bed, that loose powder can often support fragile features while you're printing. But if you're extruding paste into thin air, well, your material really needs to hold its shape instantly.
Which leads us straight to robocasting then. So what's actually happening at the printer head in this method?
Okay, think of it like a high-precision robotic arm squeezing out toothpaste. But instead of toothpaste, it's this thick ceramic-filled paste, or ink.
Right.
It just follows a digital model, depositing these lines of paste layer on top of layer. It's a technique that started gaining traction back in the mid-1990s.
Okay, so we're extruding a paste. What makes that paste, that ink, work for ceramics? It can't be just any old goo, right?
Oh, absolutely not. The paste is the critical element for robocasting. It needs very specific properties, like super specific.
Such as?
First, it has to be pseudoplastic.
Okay, fancy word. What's that mean?
It just means it flows easily when you apply pressure, like pushing it through the nozzle, but then it gets stiff and holds its shape as soon as that pressure is gone.
Ah, like ketchup.
It's exactly like ketchup. Doesn't flow till you shake or squeeze it, then it flows, then it stops. Second, you need a lot of ceramic powder packed into it. High solids loading, they call it.
Why so much powder?
Because that minimizes shrinkage later when you fire the part to make it solid and dense. Less non-ceramic stuff to burn away. And crucially, it needs to solidify or gel really quickly after it's deposited.
That quick gelling makes sense. You need the layer you just put down to hold up the next one coming on top.
Precisely. Otherwise, it just slumps.
The source mentions some variations on this extrusion theme, too. Different ways to get it to solidify.
Yeah, researchers have experimented with ways to speed up that solidification, like freeze-form extrusion, where the extruded paste is immediately frozen on a cold plate.
Clever?
Or another one called ceramic on-demand extrusion, where they incorporate drying agents or use heat to help the layers stiffen faster. It just shows the core challenge, right? How do you get that printed structure stable, like right away.
And this is where we get into the fascinating world of rheology.
My favorite. Rheology, it sounds complicated, but it's simply the study of how materials flow and deform. For these printing pastes, it's not just important, it basically determines everything.
Everything.
Pretty much. If the rheology isn't perfect, the paste won't extrude correctly, it won't hold its shape, or the layers won't stick together properly. Game over.
The source material points to a specific ingredient that plays a key role in some of these pastes, pluronic F127 hydrogels. And there's something really surprising about these.
Ah, yes. This is one of those genuine aha moments from the research, I think. Pluronic gels exhibit what's called inverse thermal gelation.
Inverse thermal gelation.
Yeah, meaning they are liquid and easy to mix when they are cold, but they turn into a gel and become stiff when they warm up, usually right around room temperature or body temperature.
Wait, hang on. Liquid when cold, gel when warm? That's completely backwards from, like, jelly or soup.
It totally is, and it's absolutely brilliant for processing these ceramic pastes.
How?
Well, you mix your ceramic powder into the cold liquid pluronic. That makes it easy to get a smooth, uniform paste without clumps. Then, as you extrude it at room temperature, it naturally warms up slightly and instantly gels, helping the printed filament hold its shape perfectly.
That's fantastic. Using a weird property to solve a problem.
Exactly. It's a counterintuitive property harnessed perfectly for this application.
So what specific rheological properties does the source say are key to predicting if a paste will actually print well? They must measure something.
Oh, they do. They highlight two main ones, yield stress and storage modulus, or G prime. G.
Okay, break those down. Yield stress.
Yield stress is the minimum force or stress you need to apply before the paste starts flowing at all. Below that, it just sits there.
And G prime, storage modulus.
G is essentially how stiff the material is. It tells you how well it stores elastic energy and holds its shape when you apply a stress, like, say, the weight of the layer being printed on top of it.
So putting it together, a good printing paste needs a high yield stress so it doesn't sag before it's pushed out of the nozzle, and a high G so the printed line stands up straight and supports the next layer.
You got it. Needs to be strong enough to resist gravity and the printing forces. The source even attempts to quantify this printability using ratios of these properties.
Trying to put a number on it.
Yeah, they found that a good paste needs a high storage modulus, G, and a high yield stress relative to how much it deforms under stress. Basically, stiff and strong relative to its tendency to flow.
And what about the amount of ceramic powder? Does adding more powder help or hurt these properties?
Generally, more powder, increasing that volume fraction, increases both yield stress and stiffness, which is often good for printability, right? And reduces shrinkage later.
What?
But it also makes the paste much thicker, harder to handle, harder to mix initially, and requires much higher pressure to actually push it through the nozzle. So it's a balancing act.
Classic trade-off.
Always. You need enough power for good final properties without making the paste completely impossible to extrude reliably.
Okay, so we've painstakingly formulated our magic paste. Let's move to printing actual parts. The source discusses making simple, solid shapes, monolithic parts out of common ceramics like alumina and silicon carbide. But even these basic shapes presented significant challenges.
It really did. I mean, getting the printing parameters right is important, obviously. Choosing a paste with high powder content, selecting the right print speed faster is generally better if the paste stability allows it, and getting the spacing between the extruded filaments just right.
Spacing.
Yeah, the source found you actually need a little bit of overlap between adjacent lines or filaments. That helps squeeze them together and eliminate gaps between them.
Okay, makes sense. But you said significant challenges. What was the biggest one?
Drying. Drying was highlighted extensively in the source as a major hurdle.
Why is drying so difficult?
Well, ceramics shrink a lot when they dry as the liquid evaporates. If the outside of the part dries faster than the inside, which it almost always does, you develop huge internal stresses.
And stress leads to?
Cracks and warping. The source shows examples of this arching effect where parts literally bend upwards as they dry unevenly. It's dramatic.
So how do you avoid that?
Very slow, very controlled drying, often in high humidity chambers to slow down the evaporation. It can take days. Another problem they ran into was parts sticking too aggressively to the build platform, which could also induce stresses and cause defects when they tried to remove them.
Huh. The source mentions an interesting little detail here. They tried printing these monolithic parts in an oil bath, which is sometimes used for other structures, but it actually caused defects.
Yes, that was a surprising finding for them. While printing porous scaffolds in oil can sometimes help support the structure, For these dense, solid parts, it seemed like the oil got trapped between the layers during extrusion.
Like little pockets of oil.
Exactly, leading to defects, pores, and the final fired structure. It just shows you can't assume a process tweak works the same way for different types of parts or structures.
Right. Okay, so after carefully printing and painstakingly drying, these parts are then fired at very high temperatures burnout to remove organics, sintering to densify. How do the final mechanical properties of these RoboCast parts stack up against ceramics made traditionally?
The source shows that with careful control over the paste and the process, robocasting can actually achieve very high densities, over 95% dense in some cases.
That's pretty good for ceramics.
It is. And they reported impressive strengths, too, around 300 megapascals for silicon carbide bars and maybe 230 for alumina, which is definitely comparable to what you might get from traditional methods for these monolithic ceramics, if everything goes right.
That sounds promising. But the source also delves into something called reliability, using Weibull analysis. Why is that so critical specifically for ceramics?
Wow, reliability. Yeah, for structural ceramics, just knowing the average strength isn't enough. Not even close. Ceramics are brittle, right?
I just snap.
Exactly. They fail suddenly, catastrophically, without warning. So reliability, which is often quantified by the Weibull modulus, tells you how consistent that failure strength is from part to part.
Okay.
A high Weibull modulus means the strengths are tightly clustered, very consistent. You can trust that most parts will fail near that average strength. But a low modulus means there's a huge scatter, and some parts could fail at much, much lower loads than expected, which is obviously dangerous if it's holding up a bridge or part of an engine.
So doing that Weibull analysis is crucial if you're thinking about using these for anything structural.
Absolutely essential. And the fact the source did this is key.
And here's where one of the really significant findings comes in. And frankly, it presents a major challenge for structural applications of robocasting. The source found significant anisotropy in both strength and reliability.
This is huge, yes. Anisotropy just means properties depend on direction. They found the strength and the reliability, that consistency varied dramatically depending on how the printed part was oriented relative to the force applied during testing.
So same part, different test direction, different result.
Exactly. Parts loaded lengthwise, parallel to the printed filaments, were the strongest and most reliable. But parts loaded height-wise, so perpendicular to the layers, they were significantly weaker and much less reliable. Lower Weibull modulus.
Wow. So the very act of printing layer by layer creates an inherent weakness, or at least a less reliable direction.
That's what the data strongly suggests.
Oh.
It tells us the printing process itself introduces features or defects that become critical depending on which way you push on the part.
What kind of defects did the source pinpoint as causing this directional weakness?
They identified a few culprits. There's always some general residual porosity left after sintering, just tiny voids. But more importantly, they saw defects between the individual printed filaments. Like, the lines didn't perfectly merge everywhere. This could leave small voids or maybe trapped air, especially if the filament surfaces were a bit rough.
Ah, the seams between the layers or lines.
Precisely. They also noted some larger powder clumps or agglomerates in the paste itself that didn't break down. The hypothesis is that these interfilament defects, especially, get kind of oriented by the printing path.
Lined up.
Yeah. And they act as easy paths for cracks to travel when you stress the part in that perpendicular direction, leading to that lower strength and lower reliability.
That makes sense. It means even if you can achieve a good average strength, this directional weakness and the variability are major things you have to consider if you want to use these parts in critical structural applications.
Definitely. You'd have to design around it very carefully.
And speaking of limitations, how does robocasting stack up in terms of, resolution and the complexity of shapes it can make compared to other ceramic printing techniques?
Yeah, the source addresses that too. Generally, robocasting is limited in resolution compared to some other methods, like lithography-based ceramic manufacturing, or LCM. LCM can achieve much, much finer details.
Why is robocasting limited?
Well, the minimum feature size in robocasting is typically tied directly to the nozzle diameter you're extruding through. And that nozzle needs to be reasonably large, often 200 micrometers or even more, just to handle the thick particle-filled paste without constantly clogging.
So you can't print super tiny, intricate things easily.
Right. It limits how intricate the shapes can be. The source shows robocast examples that are relatively simple things like grids, cubes, basic labware. And it notes that features like unsupported spanning structures or big overhangs are difficult because you're relying purely on that paste rheology, its ability to hold its shape before it fully gels or sets.
Okay, so recapping the monolithic part. Robocasting can make solid, reasonably strong parts. Density looks good. Strength can be comparable to traditional methods.
If done well.
It's done well. But it has clear limitations regarding resolution, handling complex geometry, and critically, these printing-induced defects that cause directional weakness and lower reliability.
That sums it up pretty well.
But the thesis doesn't start there. It explores using robocasting not just for single material parts, but to create ceramic composites.
Right, and this is where robocasting's ability to control the deposition path offers a potentially unique advantage.
Why composites? What's the goal?
The main goal is toughness. Traditional monolithic ceramics are strong, yes, but very brittle. They just snap catastrophically.
Right, no warning.
Composites, usually by adding reinforcing elements like fibers or maybe tiny platelets, aim to increase toughness. Toughness means the material can absorb more energy before it fails completely. Maybe it bends a bit or cracks slowly instead of just shattering instantly. More graceful failure.
And the layer-by-layer extrusion of robocasting, you said it offers an advantage.
Yes, because you can potentially align those reinforcing elements as you print. The shear forces, as the paste gets squeezed through the narrow nozzle, naturally tend to line up elongated particles like fibers or platelets parallel to the flow direction.
Ah, like logs floating down a narrow channel.
Exactly like that. You get built-in alignment.
Okay, let's talk about the platelet composites first. The source used alumina platelets. How did they even measure the properties of something so tiny? These platelets must be microscopic.
They are. And this is another example of the really detailed experimental work in this thesis. They actually developed a custom micro 3-point bending test. They used a nano indentation system inside an electron microscope to bend individual platelets, which were only maybe tens of micrometers across.
Wow, bending single tiny platelets inside in-situ. That's impressive.
It really is. It lets you measure the intrinsic properties of the reinforcement itself.
And did they find anything interesting about the platelets themselves?
Yes, quite surprisingly. Using advanced microscopy, like TEM and EDS, they found internal flaws within the supposedly high-quality platelets. Things like tiny salt impurities left over from processing, voids that actually appeared after heating them, dislocations in the crystal structure, even nanotwinning structures, plus steps and edges on the surfaces. They even estimated the average size of these internal defects.
So even your reinforcing building blocks aren't perfect. That's important to know. How did robocasting arrange these flawed platelets? You mentioned alignment.
Right. Those shear forces during extrusion through the nozzle did indeed align the platelets along the direction of flow, just as expected. And this created a very specific microstructure within each printed filament. They called it a core shell structure.
Core shell?
Yeah. In the outer shell of the filament, the platelets were highly aligned, sort of like concentric rings following the filament shape. But in the very center, the core, the orientation was more random.
Interesting. And did they figure out what controls how good that alignment is?
Yes. They showed that factors like the length of the printing nozzle and how much solid powder was loaded into the paste affected the degree or strength of this alignment. Longer nozzle, higher loading, generally meant better alignment in the shell.
Okay, so you get aligned platelets, especially near the surface of the printed line. How does this controlled alignment actually help with toughness? What's the mechanism?
This is the payoff, right? That aligned microstructure can actively interfere with and guide how a crack propagates through the material.
How?
Instead of a crack just slicing straight through easily, it's forced to deflect or tilt or twist to get around the aligned platelets that are blocking its path. You also get mechanisms like crack bridging.
Bridging?
Yeah, where intact platelets actually span across the crack, opening behind the crack tip, literally holding the two sides together and making it harder for the crack to open further, to be pulled out or broken. All these processes, deflection, twisting, bridging, they absorb energy. And that's what makes the material tougher.
So you're basically creating microscopic obstacles for the crack.
That's a great way to put it. You're engineering the crack path.
Now, to really see this toughening in action, the source talks about developing another novel testing method, an in-situ double cantilever beam test done inside in-situ. Why did they need to do that?
The in-situ DCB test. Yeah, that was crucial. See, standard bending tests on brittle materials often cause cracks to grow really fast and unstably. Zip.
Yeah.
And it's broken. You don't learn much about the process.
Right.
The DCB test geometry, combined with doing it in situ, meaning inside the SEM while watching,
Mm-hmm.
allows for slow, stable crack growth over much longer distance. You can literally watch the crack interact with the microstructure in real time under the microscope.
So you can see the bridging and deflection happening.
Exactly. You directly observe those toughening mechanisms.
Mm.
And importantly, it lets you measure something called R-curve behavior. R-curve behavior is where the material's resistance to the crack growing actually increases as the crack gets longer. This is a hallmark of tough materials with extrinsic toughening mechanisms like bridging. The longer the crack, the bigger the bridge zone behind it, the harder it is to push it further.
And they saw this R-curve behavior.
They did, and they showed how different platelet orientations testing cracks growing across filaments versus between filaments led to different R-curve behaviors. They even printed and tested a structure inspired by nature.
Oh.
Yeah, mimicking the tough, layered, rotating structure found in things like the mantis shrimp's punching club. It's called a boulagon structure. And they showed it gave good toughness, too.
That's incredible, using robocasting to create these complex bio-inspired structures specifically to enhance toughness. Okay, what about using fibers for reinforcement? The source also looked at composites with short carbon fibers.
Yes, carbon fibers are a very common reinforcement, known for adding stiffness and toughness. They explored two different paths with carbon fibers in this research. First, using them to reinforce a polymer matrix composite, a PMC.
So ceramic fibers in a plastic matrix.
Sort of. They printed a skeleton of just the aligned carbon fibers first, then infiltrated that fragile skeleton with a polymer, like epoxy resin.
How did that approach work out? What were the results?
Well, they definitely ran into some challenges, like getting bubbles in the initial fiber paste during mixing and printing, and the fact that the printed fiber structure, after burning out the paste binder but before adding the polymer, was incredibly fragile, hard to handle. But the key success was achieving excellent alignment of the carbon fibers during the robocasting printing process itself, just like the platelets.
And did that alignment translate to better properties in the final polymer composite?
It did. When they tested these fiber-reinforced polymers, they saw significant improvements in strength, toughness, and especially how much energy the material could absorb before failing, compared to testing the pure polymer matrix alone. And crucially, when they looked at the fracture surfaces, they could clearly see the evidence of the toughening mechanisms they expected fibers pulling out of the matrix, cracks being deflected by the fibers. This confirmed the alignment was working and contributing to the improved toughness, consistent with R-curve behavior in these two.
Okay, so that seems like a potentially useful application, making aligned fiber preforms for polymer composites. What about the much harder goal? Using carbon fibers in an actual ceramic matrix composite, a CMC, for high-temperature structural parts.
Yes, the CMC goal. This is where the source highlights some really significant hurdles. They tried the more direct approach here, mixing the short carbon fibers directly into ceramic matrix paste like alumina or silicon carbide, and then trying to sinter these parts at high temperatures to densify the ceramic matrix around the fibers.
And the main problem was?
That's difficult. Fiber degradation. Big time. During the high-temperature sintering process, which is necessary to make the ceramic matrix dense and strong.
The fibers got damaged?
Exactly.
Yeah.
The carbon fibers, the very things providing the reinforcement and toughness, reacted chemically with the surrounding ceramic matrix components or with the sintering additives needed to densify the ceramic.
What kind of reactions?
Well, for example, in an alumina matrix that used yttria as a sintering aid, the fibers were basically consumed, reacted away. In a silicon carbide matrix, using boron carbide as an additive, the boron acted as a catalyst that graphitized the carbon fibers, essentially messing up their structure and properties. They confirmed this using analysis techniques like Raman spectroscopy.
Wow. So the very process needed to make the ceramic part dense and strong was simultaneously destroying the reinforcing fibers inside it.
Precisely. It's a fundamental incompatibility at those high temperatures. They attempted some solutions, like trying to sinter at lower temperatures or applying a protective silicon carbide coating to the fibers beforehand.
Did that work?
According to the thesis findings, no, not really. These attempts weren't successful in preventing significant fiber degradation at temperatures that were still high enough to actually get the ceramic matrix properly densified. You couldn't get both.
So despite the promise of achieving nicely aligned fibers using robocasting, the source concludes that processing CMCs with this direct printing method faces major, perhaps currently insurmountable, challenges due to maintaining fiber integrity during sintering.
Yeah, it's a classic, difficult materials science conflict.
Oh.
The reinforcing phase and the matrix phase have fundamentally incompatible processing requirements, especially at the high temperatures needed for ceramics.
Okay, so let's try and wrap this up then. Taking a step back, what's the big picture here? What are the key takeaways from this really deep dive into ceramic robocasting based on this specific research?
Well, robocasting is clearly a compelling additive manufacturing technique for ceramics. It definitely offers advantages, like it can be relatively fast compared to some other methods. It gives you the ability to create structures with controlled porosity, which is useful. And importantly, as we saw with the composites, it offers this unique capability to align reinforcing particles, like platelets or fibers, during extrusion.
That microstructural control seems like its superpower.
It really is. It's particularly exciting for developing tougher composite materials with potentially tailored properties.
Yeah.
And there are applications where it's already useful or showing promise, things like porous scaffolds for biomedical uses, bone tissue engineering, filtration membranes, catalyst supports, or even just printing relatively simple ceramic labware quickly.
And it's a significant but. It's also really clear from this research that robocasting isn't some kind of magic bullet, especially when you start talking about demanding structural applications.
No, definitely not. It has real limitations. We talked about the resolution, the fineness of features, and the complexity of shapes you can reliably achieve compared to some other methods like LCM.
Right.
And critically, the printing process itself introduces those defects we discussed, especially those interfilament voids or interfaces between the printed lines. And those lead directly to that concerning anisotropic strength and the reduced reliability in monolithic parts. That's a big deal for structural use.
And the CMC challenge.
And the CMC challenge, yes. Plus, integrating certain reinforcing fibers like carbon into dense ceramic matrices using this direct printing and sintering method faces those major hurdles due to the high temperature reactions destroying the fibers.
So this deep dive really illustrates the intricate science and the complex engineering involved in taking a cool concept like 3D printing and actually making it work for really challenging materials like structural ceramics.
Absolutely. It highlights that it's not just about programming a robot arm to move a nozzle around. It's about deeply understanding and controlling the fundamental properties of the paste, the rheology. It's about understanding the physics of drying and shrinkage. It's about identifying and figuring out how to control subtle defects introduced by the printing process itself. And it's about overcoming fundamental materials compatibility issues at extreme temperatures.
These are the really complex, nitty-gritty problems that researchers in the field are still actively trying to solve.
Exactly. It's ongoing work.
Well, that was certainly a deep dive into the fascinating, complex, and sometimes frustrating world of ceramic robocasting, all based on this detailed research.
It certainly was. And, it leaves you, the listener, with a key question to mull over, I think. Given the incredible potential of robocasting for controlling microstructure and alignment, which is really powerful, but also considering the persistent challenges with those printing-induced defects, the reliability issues, and the high-temperature material interactions, especially for CMCs.
For what specific types of structural ceramic parts do you think this technique will ultimately prove most valuable and successful?
Will researchers find clever ways to overcome the CMC processing challenges, maybe with new fiber coatings or matrix chemistries? Or will robocasting's main structural niche remain primarily in applications where, say, controlled porosity or specific, less complex geometries are the main drivers, rather than needing the absolute highest structural reliability or intricate detail needed for, say, a turbine blade? Where will it really shine?
That's a great question, something to definitely think about. Thanks for joining us for this deep dive. Stay curious.